Good afternoon, class. So for this afternoon, I'll be discussing to you the second sample problem on convective heat transfer. Now, specifically, we're talking about forced convective heat transfer. Now, the first sample problem is talking of a heated fluid, which is air. Well, this one now will be talking about a heated fluid, which is water. Now, also in the first sample problem, there was no need for us to do trial and error in determining the temperature of the fluid that is to be heated. Now, in this case, aside from first establishing the flow regime, we need to estimate or assume an inside temperature for our fluid to be heated, which is water. So I will read the sample problem first to you, or the problem, and then we will start with the solution. So let me share the slide to you. This is our sample problem, class. So the second, so water is flowing in a horizontal 1-inch Schedule 40 steel pipe at an average temperature of 65.6 degrees Celsius and a velocity of 2.44 meters per second. Now, it is heated by condensing steam at 107.8 degrees Celsius on the outside of the pipe wall. Now, the steam side coefficient for heat transfer, that is, has been estimated as equal to 10,500 watt per square meter Kelvin. So our watt unit here should be capital letter W. Now, these are the informations that are required in the problem. So we need to calculate the convective heat transfer coefficient, this time labeled as H sub I, referring to the water flowing inside the pipe. And then letter B, we are to calculate the overall heat transfer coefficient based on the inside surface area. Okay, so that is why you have the subscript here, I. If it's based on the outside surface area, the subscript here should be O. Now, the third requirement is we are to determine the heat transfer rate for a length of pipe, which is 0.305 meters, having the same water flowing inside it at a temperature of 65.6 degrees Celsius. So this is our problem, and we will use the Jamboard in writing the given information at the same time the required, and how we're going to find the solution to the same problem. Yes, let's wait. Okay, let me now share the screen. Okay, so we will have now the given for our problem. So if we have a pipe, let's say this is our pipe. And we have water flowing inside the pipe. And we have steam here outside. Okay. As to the informations regarding water, available information regarding water that is flowing inside the pipe, okay, the problem says that the velocity is 2.44 meters per second. Okay. I think that's the only thing that is provided for water. And then it says here that your steam is at a temperature, I'd like to label this as T sub O, 107.8 degrees Celsius. By the way, class, the temperature of the water inside the pipe is given. And this is 65.6 degrees Celsius. Okay. As for the steam side coefficient, heat transfer coefficient, it's also provided. So we'd like to label that as H sub O, the value of which is 10,500. So we have watt per square meter per Kelvin. Okay. Now we are given the information about the pipe. For our pipe, this pipe is in size is 1 inch and its schedule number is 40. And it's a steel pipe. Okay. I think that's it for our given. Later, we will just go back should we have missed an information from the problem that is vital in finding the unknowns. So the first thing that is required is the H sub I, the heat transfer coefficient on the inside part of the pipe based on the water that is flowing. Letter B. So we have the overall heat transfer coefficient, U sub I. And letter C, the heat transfer rate. Given that the length of our pipe is 0.305 meters. Still, the water inside it is at a temperature of 65.6 degrees Celsius. So these are our given and required information. Now, if we go to the next page, we can map out our route to the solution or finding our required information. So for letter A, we need H sub I. And as have discussed with you in the previous lesson, H sub I is based on a particular dimensionless number. And that particular dimensionless number is also based upon the flow regime where your fluid to be heated falls into in terms of category. So even before we can find the H sub I, we first need to establish the flow of that particular fluid. In this case, in our problem, that would be our water flowing inside the pipe. So we need to determine the Reynolds number. That way we can establish the flow, whether laminar, turbulent, or something in between, which we call it in the transition flow. So as for the Reynolds number, we have the D, the velocity, the density, and the viscosity. And since we want to know the flow of water inside the pipe, the diameter that we're going to use here is the inside diameter. Okay, as to the velocity, this is already provided in the problem. As mentioned or as written in the previous page, we know already that this one is given, the velocity. And we know also that the density and the viscosity together with the other properties of the fluid, which is water, could be taken from either an appendix or a property table in section 2 of your Paris Chemical Engineer's Handbook. So what we're going to do now is look at these particular properties and then write it in here so that we need not go back again for these particular properties later on. So I'd like to show to you the slide or where the table is found, where we can get the properties of our water. Now we'll be needing also this particular table in determining the inside diameter and the outside diameter of our pipe based on its nominal size and its schedule number. I will go back to that and we'll first go to the properties of our water. So for water, we have the temperature to be 65.6. So the properties that we need from this table will be the density, which we need in Reynolds number. We also need the viscosity there in Reynolds number. We need later on the Prandtl number, and we also need the thermal conductivity of the fluid itself. This thermal conductivity will be the thermal conductivity that will be appearing in the HD over K formula later on. That is in the Nusselt number, where we will determine the heat transfer coefficient. The same thing with the Prandtl number, we need it there. Okay, so we get from this table, excuse me, four properties of your water based on its temperature, which is 65.6. Okay, now on this particular table here, you'll be getting the, I'll use a different color, you'll be getting the size of the pipe based on the inside and the outside diameter using its nominal size, which is 1 inch, and schedule number, which is 40. So the 1 inch steel pipe, schedule 40, will have an outside diameter of 33.4 and an inside diameter of 26.64, all in millimeters. So this we will be needing later on. Specifically for now, we'll be needing the inside diameter in determining the Reynolds number together with the velocity, the density, and the viscosity of water. So let me go back to our Jamboard. So this is our Jamboard now, and we will write the values that we have read in the tables shown to you a while ago. So for the inside diameter class, we'll have 0.0266. This is already in meters, previously read in millimeters. Then the velocity is 2.44. And the density is 980 kilogram per cubic meter. Notice that I'm not anymore writing the units because it's understood that if I'm working on SI sets of units, they will all cancel each other because this one is a dimensionless number. So it's divided by the viscosity. So the viscosity that I have shown to you a while ago based on the 65.6 degrees Celsius temperature of water is 4.32 times 10 raised to negative 4 Pascal second. Now, if we have this process, the values, our answer for the Reynolds number is 1.473 times 10 raised to 5. So since it's like, this one is like 100,000 already, we can say that our flow is turbulent. I'm sorry. Okay, the flow is turbulent. So we conclude that the flow is turbulent. We know also in the previous lesson that if the flow is turbulent, the dimensionless number that we're going to use is the Nusselt number. And the formula for that is actually H D over K. Now, since H in the original formula for Nusselt number is HL, this time we'll write it as HI because the heat transfer coefficient that we're going to consider here is based on the inside part of the pipe where your water is flowing, the fluid that is to be heated. So this will be equated to this particular empirical set of values. So how this particular formula came about, it's based on data gathered through experiments. So these are the parameters that appear in our formula. Okay, so this is our Reynolds number. This is our Prandtl number. This is the viscosity of the water, the bulk viscosity of the flowing fluid. And this is the viscosity based on the wall temperature. Okay. Now, this one, the diameter is still the inside diameter of the pipe. And the thermal conductivity constant was the thermal conductivity constant that I have underlined in the table that was shown to you. So from this particular dimensionless number, the Nusselt number, will be able to find the H sub I. And I'd like to write here the corresponding formula for it. So we have this one. We'll transfer the K and the D here. So this would be K over D. Specifically, I'll use the D sub I. Okay. Now, we're done with this first equation in determining the flow of our fluid, whether it's turbulent or laminar. And this is our second equation. Now, let's check in our second equation what we know and what we still do not know. Okay. Now, we have already the Reynolds number. We have already the Prandtl number underlined a while ago. We have already the bulk viscosity of water based on the 65.6 degrees Celsius temperature. And we have also the thermal conductivity. And we have also the inside diameter based on a table also, using the nominal size and the schedule number of our pipe. Now, the question is the viscosity based on the wall temperature. So where will we be getting this particular viscosity based on the wall temperature? This wall temperature class, by the way, will be based on the temperature of the steam. So let me go back to the previous page. So we have steam here, and this is the wall. So more or less, the temperature of your wall, of your pipe, will be the same as that the temperature of the steam. So in here, in the viscosity based on the wall temperature, the temperature that we will be using will be that of the temperature of the steam, which is 107.8 degrees Celsius. Where are you going to get this viscosity? It's still referring to that of water, so you're going to read it from the same table. Okay, let me just check class. New share. If this is our table, you are to get the temperature at the wall based on a particular assumption. So you're still going to use the same table. Now, normally, class, what would be used here is the simple assumption that I have mentioned a while ago. The temperature of the wall will be the temperature of the steam, or that is the heating medium outside of the pipe. But there is a suggestion, class. This is the suggested value, because you will later on go back to the value that you got, on the assumed value that you got, and check whether the temperature that you use is acceptable or not. The author of our book suggested that the wall temperature that you're going to use will be one-third the difference of the wall temperature if you use the temperature of the steam and that of the bulk temperature of the water. Again, you get the difference of the temperature of the wall basing on the temperature of the steam and that of the water inside, and you divide it by 3. That would be the first trial temperature that you will use as a basis in determining the viscosity of the water at the wall or inside the wall of your pipe. So it says here, it's just but a suggestion. You get the difference of the assumed temperature of the wall, which is that of the steam and that of the bulk water, and you divide it by 3. Okay, So first, we will get that particular temperature. So I'd like to go back to our Jamboard. So actually, in the process class, you assume two things. Okay? You first assume that your wall temperature is 107.8 degrees Celsius, but in getting the viscosity at this particular wall temperature, you will get this one. The difference of the wall temperature, which is assumed wall temperature, which is 107.8 degrees Celsius, and the bulk temperature of the water or of the medium that you are to be heating, and that's 65.6. And then you are to divide it by 3. The corresponding temperature that you will be getting, in this case, which is more or less around 80 degrees Celsius, will be the basis. This would be the basis in getting the viscosity at the wall. So actually, you're not using this one. Why I say you're not using this one? Because you assume that the temperature of your wall in the first place is 107.8, which is not. So you use the difference of these two, 1/3 of the difference of these two, and that's the basis for the temperature that you will read for the viscosity at the wall. So this 80 will be the one that you're going to use in here. So again, I'll go back to our PowerPoint. So it's difficult, but you have to bear with me. So you have to look for the 80 here. 80 is somewhere in here. So you need to interpolate class. So I will not anymore show to you the interpolation, but since 80 is somewhere here, that's where the 80 is. So you need to use these values or these values and then get the corresponding viscosity here. And since the sample problem already gave us that, so we might as well use it directly. Okay, so I'll go back to our Jamboard. So using this particular temperature and showing to you the table where you get it, that there's a need for you to use interpolation. The viscosity at that particular wall temperature is 3.56. This is just to save us time. Times 10 raised to -4 Pascal seconds. Okay, you will use this viscosity at the wall based on this assumed temperature of your wall. Actually, that's the second assumption already. Okay, you will have a way of checking this later on as we proceed in the solution. Okay, now knowing the mu sub W, viscosity of the wall in here, so you have everything known already. Okay, so everything I have checked already, that would give you the H sub I, the one that is being asked in letter A. So from equation 2, that way we can save time. Again, anyway, I have shown to you already the formula. So this is our equation 2. If we substitute all the values that I have shown as well, you will be getting this H sub I value. Okay, so the H sub I value would be 13,324 watt per square meter Kelvin. So this is the first required information. Okay, the heat transfer coefficient based on the inside surface of the pipe. Okay, so take note that we have assumed something, so we will check later on whether our assumption is correct. Now we go to letter B. In letter B, you are asked to determine the overall heat transfer coefficient U sub I. So in the first place, now you will think, what particular formula will I use? That way, I'll get this overall heat transfer coefficient U sub I. Now, in the previous discussion, I have presented to you a formula for heat transfer having the overall heat transfer coefficient. So I'll use now the I here, meaning I'm using the inside properties of the pipe. And I have here T sub O minus T sub I. Okay, that is our formula for heat transfer based on the overall heat transfer coefficient. This same formula is actually equal to the fundamental formula for heat transfer, which is driving force, temperature difference, divided by resistances or resistance if we only have one. In this case, we are to account for resistances, conductive resistances and conductive resistance because we only have one in the form of the pipe, and convective resistances based on the inside film and the outside film coating your pipe wall. Okay, so we have now summation of resistances. Now, in this case, class, we are not really for now interested with the Q, but rather with this particular relationship. That U sub I, A sub I, times the quantity T sub O minus T sub I is equal to this. Now, I think you could see what is common between two equivalent quantities. And you see that your T sub O minus T sub I is present here, and it's also present in here. That would leave us with a simplified relationship that would lead us to the U sub I that we need. And that is your U sub I, A sub I is equal to 1 over summation of resistances. Okay, and since we are interested with U sub I only, we might as well write U sub I is equal to 1 over AI summation of resistances. Now, for now, we don't know anything about this, the inside area, and we have the summation of resistances. But we will go back to this formula by labeling this first as our third working equation once we know already these two. So we'll try to find first the inside area. So the inside area of your pipe, of course, will be based on the area of that rectangle when you slice your pipe. Like it's a cylinder, but if you slice it on the side, what you will be forming is a rectangle. Okay, so that rectangle will have pi dl. Okay, pi d for the circumference and length of the pipe. Specifically, now we're interested only with the inside diameter. So we will substitute the values because we already know this one. So we have here pi. As for the inside diameter, we have, a while ago, it was shown to you as 0.0266. And the length that we stated in which we're going to base the heat transfer rate would be the same length that we will be using here because we'll be using anyhow the overall heat transfer coefficient later on in determining this Q. Or actually, we can also use the summation of resistances together with the driving force. So in this case, I'll be using the length that is stated in the problem, which is 0.305 meters. Now you have already the inside area, or 0.0255 square meter. So this is the inside area of your pipe, or the inner part area of your pipe. So we know this already. Okay, so we know this one already. Now, the next thing that we are to determine is the summation of resistances. And when we speak of resistances, so I have mentioned it a while ago, we have to account for one conductive resistance and two convective resistances. So we go to the next page in determining this particular resistances. So when we speak of the conductive resistance, this will be our formula for that. So R, or let's say I'll have here due to puro man na sila galit tanan C. So due to conduction. Okay. Resistance due to conduction, and that's taking into account the type of material that we have, that would be using the formula outer radius minus inner radius divided by the product of K times the area. Now, the area that is labeled in this formula class is LM. But this is not to be misunderstood as the log mean area, because the log mean area is labeled as A with a subscript ALM. If it's just LM class, it's just a, shall I say, arithmetic mean of the formula for the area, not the log mean area. Okay, I'd like to show to you the previous slide on conduction wherein the labeling for the area, log mean area, is not this one, because this is the common mistake of my students. Whenever they see an LM here, especially on the topic of convective heat transfer, they misunderstood that the area that is going to be determined here is the log mean area. No, class, the log mean area is written in this form. So I'd like to show to you a slide, new share, where we have discussed this one. So the log mean area is labeled as A with ALM. Okay, but if it's just A with the subscript LM, it's just the arithmetic area that we are determining. So log mean area is like that. So you have to remember that. Okay, now I'll go back to our board. So this area that we have here is just the mean area, okay, not the log mean area. So we will substitute the values here if they are already available, or we might as well check whether we have them already or not. Okay, I'll have a different color because I use the red already. So outer radius is your outer diameter divided by 2. Inner radius is your inner diameter divided by 2. This one should be the thermal conductivity of steel. And this one we need to determine first. And since we don't know any, we can solve this for now. I will go back to this. We'll label this one as equation. So what's our equation? This is already equation 4. Now, where are you going to get the thermal conductivity of steel? In your Paris Chemical Engineer's Handbook, you may have the thermal conductivity of steel read from a property table. Okay? Now, for this one, in this case, for us to be for us to get it in a faster way, I will show to you in the slide in which particular appendix in John please you can read that one. Okay? Okay, let me check. Okay, this is the particular appendix in John please where you can find the thermal conductivity constant of commonly used materials. So in your handbook class, this has also an equivalent. So for steel, you have here, we'll use the steel which has 1% carbon, and the thermal conductivity constant is this one, 45. Okay. Actually, even if it's on a different temperature range, it's still 45. So this one is 100 degrees Celsius, and this one is for 200 degrees Celsius. This one, this 43 is for 300, and this one is for 18 degrees Celsius. So we can use the 45 value for the thermal conductivity. Now, you can use a value that is more specific for steel, the one that is available in your handbook. If the problem is silent about the percentage of carbon in your steel, you may assume that it's 1% carbon. So in this case, we can use the 45 value, 45 watt per meter Kelvin value for the thermal conductivity of our steel. Okay? So again, we go back to our board. And we'll have this check because we know this already. Okay. Now, as for the A, arithmetic area, so that would be just getting the outer area and the inner area divided by 2. That would be our arithmetic area. So I will solve it in here. So I'll use the black ink now. You have A, LM. So in terms of arithmetic area, that would be pi DO plus DIL divided by 2. Okay, and we can substitute the values of the inside diameter and outer diameter rather in this particular formula. So we have pi, and I will read it from here, the diameter. So for inside, we have 0.0266. For outside diameter, we have 0.0334. We divide this by 2, and we multiply this by the length. Okay, so our arithmetic area here is 0.0287. Of course, this should have a unit in square meter. Okay, now we know everything here. We can have this checked already. And if we substitute values to it, so I will not anymore write the value substitution here. So I'll just write from equation 4, R conduction is equal to, so you substitute the outer radius, the inner radius, the thermal conductivity, which is 45, and this value for the arithmetic area, which is 0.0287. So the R resistance due to conduction would be 0.002633. Okay, this is just one of the 3 of the resistances that we need to account for. So we know it already. Now we go to RI. So taking into account the film coating the inner part of the wall where your water is flowing. And the formula for this is 1 over H sub I, A sub I. Okay, the H sub I was already given in the problem. Rather, it was solved a while ago in letter A. So we can determine now the A sub I. So let me just check this one. This was already determined in A. So we can determine now the A sub I. So let's have this as our equation 5. So if we'll solve for A sub I, I'll just place it in here. So your H A sub I, that would be pi dl. Okay, the transfer area based on the inside diameter. So I'm just going to substitute the inside diameter here. And we have the length. So your A sub I is 0.0255 square meter. Now, knowing this one, you can now solve for R sub I. So we know the A sub I already. So I'll just place here from equation. So we have R sub I. This is convective heat transfer resistance in the inside part of the pipe that will have a value of 0.002943. Okay. Okay, so now we have the conductive resistance. We have the convective resistance on the inside part of the pipe. Now we can go to the R sub O. So your R sub O would still be having the same formula as R sub I, but this time, of course, you will have HO, AO. Now, HO, we know already, it's given. It's based on that of the steam on the outer side of the pipe. And this is, I think equation 6 already. So we need to determine first A sub O. Okay? Just like what you have done in here. Okay? You determine A sub O so that you can get your R sub O. The same thing, you will be using pi dl, but this time this should be d sub o. And you have pi. Our d sub o was shown to you already to have a value of 0.0334. We'll use the 0.305 as well. And you'll be getting a value for a sub o, which is 0.0320 square meter. Now you know this, you can substitute it here back in equation 6. So substitution to equation 6. So from equation 6, you will have an R sub O value. You substitute AO and HO. You will have an R sub O of 0.002976. Okay. Now your resistances are complete already. So you have your R sub O, you have your R sub I, and you have your R due to conduction. Okay. The resistance offered by the pipe itself. So what you're going to do next is solve for your series of resistances. Why we solve for that means, because you could see in here in our formula number 3, oh, I solved already AI. In formula number 3, you need the summation of resistances together with the inside area of the pipe to get what is required here in letter B. Okay, so we will just do that. So we'll get summation of R, or we can go straight to substitution to this particular formula. So from equation 3, here in this page number 6, so from equation 3, your U sub I is equal to 1 over, I think I wrote here the inside area, 0.0255. So 0.0255. This needs to be multiplied to the sum of all resistances. So we'll have Ri, 0.002943. Then we have the conductive resistance due to the pipe wall, that is 0.002633. And the last one will be the resistance here based on the steam side fluid. And this is 0.002976. Now in here, you'll be able to get a U sub I value. The U sub I value that you will be getting here is 4,586 watt per square meter Kelvin. So everything always starts with the formula that we are to use. Find the parameters that we need to substitute in that particular formula, and then solve for the unknown information. So this is the overall heat transfer coefficient based on the inside area of the pipe. Notice that its set of units is the same as that of the H, the heat transfer coefficient. Okay, it's also in watt per square meter per Kelvin. Now, we go to letter C. That's the last requirement that we have. But before we go to letter C, class, we need to determine whether the assumption that we had, remember, we had this assumption. We had the assumption that the wall temperature is 1/3 the difference of the assumed wall temperature if we consider the steam temperature on the outside part of the pipe and the bulk temperature of the water. Okay, that's our first assumption. Now we will check whether we can go forward or we need to redo this particular assumption. But by the way, this is suggested by the author of the book, meaning it's safe to assume it this way. The value that you are most likely to get when you use this suggestion is nearer the actual value that you will be later on getting when you do the checking. So before we go to letter C, we will first check, okay? We'll do the checking whether the 80 degrees Celsius is acceptable as the wall temperature where we based our viscosity with the subscript W. Because if it's not, then our answer, of course, be affected. So we'll go the checking. We'll do the checking. Now we know that for heat transfer, the Q that we have, whether we base it on the summation of all resistances, so I'll use here summation of R, and of course you have the driving force here, the outer temperature minus the inner temperature. This is steam temperature and this is water temperature, will also be equal to, if I will simply account for the resistance in the inner part of the pipe, where the temperature of the fluid, the T sub I, and the pipe wall temperature will be the temperature difference that I will be placing here as the driving force. Again, I will explain, because this is fundamental in heat transfer, that whether you are accounting for the heat transfer rate using the summation of resistances, or whether you're only using a particular resistance where your heat is to pass through, the same amount of heat passes through these resistances, whether overall or just one resistance to consider. Now, why use this particular relationship for heat transfer? Because this is true, fundamental for all heat transfer that is. It's because it would be able to make us, in this particular problem, check whether the TW that we use, which is 80, based on the assumption that is suggested also, is acceptable. Using the what? Using the summation of resistances that we got and the inside resistance only due to the convective resistance of the film coating the inner part of the wall or the inner part of your pipe. So we will do that just now, just to check whether it's okay for us already to proceed and there's nothing to redo in what we have done. Okay, so as for the TO, outer temperature, that would be 107.8. Inner temperature is 65.6. So this would be the temperatures that I'm going to substitute here. So we have, 107.8, 65.6. We divide by, so if we have summed up the resistances in here, so I will just get the summation of resistances that's available in here. So we want to do the computing. This would be 0.008552. Okay, and we have here T sub I, and we have the temperature at the wall. This is actually the delta T, the temperature difference. I might as well write it now as delta T. And we can go back later to checking what is the T sub W. And then we have here the R sub I only. So the R sub I only is 0.002943. 0.002943. In this process class, you are able to find the delta T. And the delta T value that you will be getting here would be 14.5 degrees Celsius. What is this 14.5 degrees Celsius? That's the TI minus TW. or which of the two is greater in the first place? Is it the bulk temperature or is it the water temperature? It is the wall temperature. Which do you think would be greater? Is it the temperature which is 65.6 or the wall temperature? I think that would be the wall temperature because your wall in the first place is where the heat coming from the steam on the outer side of the pipe will be coming in. So we'll have delta T to make the positive difference will be temperature of the wall minus the temperature of the water. So if this is 14.5, the temperature of the wall should be subtracted by 65.6. Okay, now we'll have T of the wall would be the sum of these two, and this would be like 80.1 degrees Celsius. Okay, so the manner of subtracting this one in here is very important because if you will write it like this one, T sub I minus TW, although we are only concerned here with the absolute value of the heat that was transferred, it would be not getting 80 because T sub I actually is smaller than the temperature of the wall. So you will be getting a negative value in here. So let me just erase this one so as to not to confuse you. Anyway, when you solve later on for heat, it should be the magnitude that you should only be concerned of. Otherwise, you place a negative here on the temperature difference if you will write it in the manner I have written it. So as not to confuse you, the temperature difference here we will make all the time, we will make it positive. So wall temperature minus inside temperature. Okay, so that you will have it agreeing here. So you have 80. Now, is this a check? The wall temperature is 80.1. Is it the same as the assumption that we had used in getting the mu sub W? Because if it's different, this one will be affected. If this one will be affected, the H sub I will be affected. If the H sub I will be affected, the R sub I will be affected. So everything is a chain process. The error here will be inputted also in your H sub I, and everything will also have some degree of error. Now, I think since we have assumed that it's 80 degrees Celsius for the wall temperature based on the suggestion also, and upon checking here, it's 80.1, it's okay to proceed because your error is very small. Even if you're going to solve the error here, I think it's very, very minimal. Okay, so assumption, I place here a conclusion. Assumption is accepted. If not, you will have to assume a new temperature again, determine again U sub W, determine again HI, determine again RI. So, and determine everything. So summation of R will be changing as well. Okay, so there's no need for us to worry about the wall temperature anymore because anyway, what we got here is near the one that we have assumed. With this already checked, we can now proceed to letter C. So we will solve for the heat transfer rate. Anyway, it's already only substitution because we have already defined everything here. Okay, so we go to letter C. So for your Q, you either use T sub O minus T sub I over summation of R, or you use, the formula in which you have this one. The U sub I. Where is the U sub I formula, by the way? Where we get this one. Okay. Q equal to UA, also this one. So we can use that one. Anyway, they will be the same. So you can have UAI TO minus TI. If you use this one just for checking whether the value that we have here for the U sub I in letter B is workable, you may do so. So your U sub I, where is that thing that I have? This is 4586. So if I place in here 107.8 minus 65.6 divided by summation of resistances of 0.008552. This should be also equal to UI 4586, the one I just read. The area, inside area, 0.0255. Okay. Just place it in here because it will not fit already. So you will have here T sub O, which is 107.8 minus the 65.6. Whether you use this one or this one, you'll be getting the same rate of heat transfer. So the rate of heat transfer will be more or less 4,935 watts. So this is our answer for the third requirement in the problem. So for the heat transfer rate, that would be 4,935 watt. Okay, so if we go back as to the unknowns to recheck, our first unknown is HI. Our second unknown is U sub I, and our third unknown is Q. So your HI is this. Using this first, the assumption that is suggested. Your UI, based on that assumption as well, because your HI will be used in determining the RI. So your UI is 4,586 watt per square meter Kelvin. And we check before we proceed whether our temperature, assumed temperature, is acceptable, and it is. So now it's okay with us to determine the last requirement, which is just a substitution of the rest of the things that we have solved before this particular part of the solution. So it's 4,935 watt. Okay, class, so we will continue with the sample problems. I will just announce whether we'll have a new recording for a new sample problem in our GC. If you have any question concerning this problem, don't hesitate to message me in Canvas or even privately through Messenger. So bye for now, class.